Okay, hello everyone. So we are now recording the class. It is great to have Professor Gasarch to continue about approximation and approximation algorithms. And then later we will continue with fixed parameter algorithms in the rest of the class. So good. So I think here I leave you and Professor Gasarch. And Bill, do you want to share page?
Here we go. Okay, can you all see it?
Yes.
Okay, very good.
I can see it. I think they should
okay.
be able to
so,
see.
So let me say this now. Also, people watching the recording is that yeah, on Monday there'll be an updated version of the book online at the usual site, and then you have bug reports due on December 2nd. So email your bug reports to both me and Mohammad, because your typos or more serious corrections will make the book a lot better. Okay.
Yeah.
So
good.
Okay, very good. So now
I think you can just do that, and then we'll be back.
Yes, very good. Okay, and okay, so I'll now begin with I want to clear up a point from before. These are slides that I just made yesterday. I was very happy to make them. That is, somebody asked, gee, if SAT is in PCP O of 1, O of log n 1/2, doesn't that mean SAT's in P? A fair point. So these are still the points here. I now have quite a few slides investigating that. So I will now show you why SAT is not in P. Or, well, that'll be awesome. I will now show you why the PCP theorem does not imply SAT is in P. Okay, so yeah, this is the PCP theorem. PCP is an O of 1 query bits, O of log n random bits, and remember it's if X is in SAT or X is in A, I suppose. Yeah, if X is in SAT, then there is a way of setting the query, setting the oracle. So it's always going to say yes. If X is not in, the probability that you're fooled is less than equal to half, although we could drive it down to 1 over 100, whatever. Okay, stated nicely, why does PCP theorem not imply P equals NP? Well, I'll make up numbers to avoid notation. I don't want to put in like C's and D's. Let's just say A is in NP, and A is in PCP for 5 log n 0.1. And we think, and I think some people thought, oh, well, we can just run all possible oracles and random bits, and that'll help us figure out whether or not X is an A. Yeah, so I want to know whether X is an A. But before that, though, how many queries are possible? Well, if you look at all possible, bit sequences of queries and random bits, there are 4 queries and 5 log n random bits. So there are 2 to the 4 plus 5 log n, or 16 to the 5th possible queries. That's P of n. We'll call that P of n. These are the number of possible queries. So you could ask about, is the 8th bit 1? Is the 12th bit 1, etc. So 1, 2, 3, 4, P of n. So happy with that. Okay. Now, number of random bits is actually ceiling of 5 log n. We'll just call it L of n. So I'll just use P of n and L of n for the rest of the talk, for the rest of this part of the talk. P of n is polynomial, L of n is logarithmic. And if X is an A, there exists a Y of size P of n, a tau of size L of n, so that my x tau, that should be equals 1. When if X is not an A, then for all possible Y's, the number of taus that equals 1 is going to be less equal to 0.1 times 2 to the L of n. So only a small fraction of the random bits are going to actually make you accept. Okay, so are we happy with the setup? Again, don't be shy. There's only 3 of you, so when I say are you happy, I really want you saying yes so I can move on. So, okay, Yin Cao, happy with this?
Yeah, I'm happy.
Okay, very good. Now, so idea 1. Well, goodness, let's just try all 2 to the P of n y's. That's no good. P of n is like n squared. Well, in our case, n to the 5th, or roughly. That's too many. What you were probably thinking of was more this. Let's try all 38 long bit sequences for answers. 38, no, sorry, that should be 4. Originally I had 38. That should be 4-bit long sequences. So let's just try all 4-bit long sequences of answers. next slide, we'll see how that would actually work, or how to do that. Okay, so let's try all, let's see, 5 bits. Yeah, 5. Okay, fine, 5 bits. Okay, so let's see what happens. Take n so that L equals 8. So this is very concrete. We're looking at 5-bit answer sequences and 8 bits of randomness. Okay, so let's try. Let's actually look at the sequence 0, 0, 0, 0, 0. We can do that. We certainly can. Okay, we'll answer this. This means that the first query will answer one way. And let's just say, okay, so we're going to run the machine with, say, random bit 0, 0, 0, 0, 0, 0, 0, and query answers 0, 0, 0, 0, 0. What does that mean? Well, the machine first asks, what's the 23rd bit? And we'll say 0. Then tools along, says, what's the 32nd bit? We'll say 0, etc. So we have 23, 32, 38, 40, 74. And in this case, the answers are all no. And let's just say, let's just say the machine says X not in A with this. We'll then try 0, 0, 0, 0, 0 with 0, 0, 0, 0, 0, 1 as a random sequence. And now you are not going to ask about 23, 32, etc. You're going to ask about 8, 15, 21, 47, 98, etc. And let's say the answer is yes. So this could happen. So for so let me ask: when some of you said, "Can't you get?" Is this what you had in mind when you thought about trying to prove that A is actually in P? Is this what you were thinking of doing, or does it make sense that pushing your thoughts further, this is how you would try to get A in P? Amin, happy with that?
Yeah, sounds good.
Okay, very good. Okay, and so you're curious why this is not going to help us. We can do all this. We really can do all this for all query answers length 5 and all random bits length 8. But notice very carefully that every different random sequence gives you different queries you're actually asking. We're not always asking the same things. So in fact, what we'll do is we would then take all the times you get a yes and put it in a table like this. So again, these are all made up, of course. Let's just say that on bit answers 0, 0, 0, 0, 1, and these random bits, these queries, you said yes, and all this. So and again, you could do this. This is when I say we're not going to end up getting A in SAT. This is actually the point you could do. You really could. The number of the bit answer sequences are 5 long. The random bits answers are generally L of n long, but that's not that many. So this is a polynomial length table. But the question is, now what do you do? Because realize the key thing is that, look at the third column. You ask different queries. Now, let's see now. We're wondering, can we actually get a consistent Y? And is there a Y so that for all tau in 0, 1 to the 8th in our case, there's a sequence of 5 query bits that is consistent with Y, and if so, X is an A. If not, then not. So the thing is, we're now wondering, well, 23, 32, 38, 40, not in, 74 is in. That is consistent with 23, 30. For example, the first and last row are consistent with each other. That is, both say 23 is not in. This one says 32 is not in. This says no comment on 32. That's fine. 38, they both say is not in. 40 is not mentioned here. 41 not mentioned here. 74. So do we see that if you try to piece together the first and 7th strings, you will get a consistent Y with 23rd bit is in, 23rd bit yes, 32nd bit yes, 37th yes, 38th yes, 40. No. 41st no. 41st yes. 74th, yes. Yes. Okay, good. So, we could patch together the first and second bit. We're trying to find some Y that is, we're trying to find some Y that is consistent with all the here, random bits. We want to have every single sequence of random bits, maybe 0, 0, 1, 1, 1, and 0, 0, 0, 0, 0, 0, 0, etc. is a yes. And has some queries. Maybe, so the point is we want to patch together all these sequences of queries. So let me say more carefully. For every single sequence of random, we want to do the following. for every sequence of random bits, find some bits sequence that works. Then take together all those bit sequences and find the queries they imply answers to. And can we patch that together to one big Y that actually takes care of all those queries? Can you do that? So if we formalize this, we have what's called a string consistency problem. But roughly speaking, we have, given a set of substrings, is there some big string that has all those as substrings? That's some kind of string consistency problem. And that problem is, wait for it, NP complete. Darn. So in fact, what that means is that the proposal you had, or you were thinking of, for trying to get A in P leads you to another NP complete problem. I think the key confusion was that bit answers, if you say, I'm going to answer with 0, 0, 0, 0, 1, that implies one set of queries, when it's, for example, 0, 0, 0, and some random bits, 0, 0, 0, 0, 1 with different random bits, different set of queries, 0, 0, 0, 1, 1 with random bits, different set of queries. So you can't just say, oh, you're not saying, I'll answer 1 a certain way, 2 a certain way, 3 a certain way. You're saying, I'll do the first query a certain way, etc. Okay, so NP complete. This means, so we see that now, it didn't actually get us P equals NP. Now, so pro of all this. So what am I to make of all this? The good news is that means the PCP theorem does not show P equals NP. Hence, our book will not be obsolete upon publication. The con is, well, if we did get P equals NP, we could solve lots of things quickly. Although let me ask you, Eshwar, would you want to be in a world where are you hoping P equals NP? Yeah, good. Eshwar, yeah.
I think then we can solve a lot of problems.
Yeah.
We can get hardness of a lot of
no, we can't.
Problems like recoloring, max recoloring, everything.
No, if P equals NP, all those go into P, yes?
Yes.
So if P equals NP, we don't get hardness, we get everything's easy.
Yes, everything belongs to polynomial time.
Yeah. So would that be good?
I mean, yes, I think.
No. This is not a quiz. This is an opinion question. Let me tell you, the good news. You're right. First off, a lot of problems would be easy, which is good. However, unfortunately, we also would have cryptography would be bad, and also Ying Kang's working on quantum computing. Though the entire field goes away. So sorry, Ying Kang. Okay, now, I wonder, however, the PCP theorem can be interpreted as at least NP is easier than we thought, and hence maybe evidence P equals NP, although nobody thinks that way. Okay, so any questions on why the PCP theorem does not give us that P equals NP? Okay, and let me just ask you a fun question. Yeah, this first sequence I have, yeah, 23, 32, 38, 40, 74. That's actually an important mathematical sequence. Do you know what it is? Anyone know? Okay, I will leave that for you to ponder for later. Okay, and now second part of the lecture, that was just more topping off last lecture. Okay, so yeah, last lecture I proved I gave you the PCP machinery, explained it to you, and also some today. And then I also used the theorem, the hard theorems about PCP to prove clique hard to approximate. And I know what Kevin, Kevin, is that your name?
Yeah.
Kevin? Yeah, Kevin, I know what you're thinking. You're thinking, great. Once we had SAT was hard, we could then get a lot of things hard. Now that we have clique is hard to approximate, we can now get a lot of things hard to approximate by reduction. Is that what you're thinking?
Yes, it can be something useful.
Yeah, I mean, whether you're actually thinking it or not, it's certainly a reasonable thought. Right?
Mm-hmm.
Unfortunately, it's not true. Sorry. It turns out that a clique is not that useful for proving that many other things approximable. But a different problem is max 3 SAT actually is useful. And I'm not going to go into PCP from max 3 SAT, but take my word for it. We'll get into what it means later. We're going to actually assume max 3 stat is hard to approximate and use that to do reductions that other problems are hard to approximate. So this is more back to your, I think this is more familiar to you. We're going to do a lot of reductions that's more familiar to what you're used to looking at. Okay, but first I got to define some terms. There are two kinds of problems. There are max problems like max 3 set clique. We want a large clique. Independent set, we want a large independent set, max problems. Min problems, vertex cover downranking set. And we'll define terms just for max problems. For min, it's similar. Okay. And alg, as usual, means a poly time algorithm. And we also will mean it to find solutions. Yeah, we kind of want to really, when I say I have an algorithm for clique, I kind of mean I want to actually find the clique. Okay. We'll assume P is not NP. And let A be some max problem, like max 3 stat. I better tell you what it actually means before I go on. Max 3 stat is you're given a Boolean formula in 3 CNF form, as usual, like you are for 3 stat. And normally you say, oh, I want to satisfy all the clauses. Here you're saying I want to maximize how many clauses I can actually satisfy. So have you seen max 3 stat before? Okay, Yin Kang?
Yeah, probably.
I mean in this course.
Oh, in this course? I don't quite remember.
That's fine. Well, to be fair, I understand. After all, it is 8 in the morning. Anyway, okay, but however, Yin Kang, do you have it now? You have seen 3 stat, of course.
Yeah.
Yes, and you can imagine that it's reasonable to ask, gee, maybe I can't satisfy a formula. Maybe I can satisfy, like, say it has 12 clauses. Maybe I can satisfy 10 of them, say, something like that. You want to maximize number that you satisfy. That makes sense?
Yeah, sure.
Yeah. Okay. And alg will actually find a solution that does that, the assignments, that maximizes it. Benefit of, yeah, so if A is a max problem, alg is an algorithm that finds solutions. Benefit of alg is how good alg is, the number of clauses satisfied. So, for example, I might the following is it'd be a nice theorem. There is an approximation algorithm that will, given a formula phi in 3 CNF form, find an assignment satisfying, say, 3/4 of the optimal. That, oh, you could have satisfied 1,000 of the clauses. We can't quite do that, but we can satisfy, say, 9/10 times that. Not 9/10, say 900 of the clauses. That'd be good. So benefit be 900. Okay. And for min, we'd use cost. Okay. Now, approximation. So, something is a C approximation algorithm if the benefit is at least 1/C times benefit. So that turns out to be easier to, the 1/C is kind of a funny thing, but it turns out to be easier to find things this way. Anyway, the point is that, oh, I can do somewhat well. I can do within 3/4 optimal, say. Okay. And a polynomial approximation scheme is going to be that on input x comma epsilon, I can do really well. I can do 1 minus epsilon opt. So, for example, for max sat, here's what it would say. This is actually not true. Let's see. I mean, give me a small number epsilon.
0.17.
0.17. Oh, okay, fine. Then wow. If a problem is in P, has a p-task, it means, oh, there's an algorithm that will, on input x, give me in polynomial time, find me something that's within 0.17 times optimal. Say you had said 1/billion. Great. 1 minus 1/billion times optimal. That's pretty good. So we would like epsilon small. That's the good news. The bad news is you fix epsilon at, say, 0.17. That plays into the runtime. So the runtime can depend on epsilon. So you can have runtime, say, n to the 2 to the 1/epsilon squared. Okay, I mean, what is, you said 0.17? Is that right?
Yeah.
What is 0.17 squared? All right, get a calculator.
0.289.
And what's 1 over that?
No idea.
You have a calculator, come on.
Okay.
So what's 1 over that?
3.46.
Right. So we'll call it 3.4. Fine. So this is going to be, so the algorithm time n, this is the 2 to the 3.4. So that's roughly n to the 8th. And had you said 0.01, it would be a lot worse. So the good news is for every epsilon, you have a better and better algorithm for the problem, a better approximation of the problem. The bad news is you pay for it. That is, the better the approximation, the longer it takes, although it's still polynomial. However, so you might think, oh, he's going to give us some p-tasses. Remember, this is a course on lower bounds. I'm going to show problems. I'm going to prove to you certain problems don't have a p-tass. So for example, it is known that max 3 sat does not have a p-tass. That is, there's a certain limit to how well you can do. Like more is known. I'll get into that. So let X be a, oh yeah. So we say A itself is in p-tass if it has a p-tass. Aha. Now, it's an APX. If there is a constant, you can do better than that constant. To realize this is a hierarchy of a p-tass. This is the gold standard. You really want a p-tass. You can do 0.99 times optimal. You can do 0.999 times optimal. That's great. APX means, okay, we can do, for example, 3/2 times optimal. Sorry, not 3/2. Yeah, say 0.9 times optimal, for example. But maybe we can't do any better than that. So the distinction is p-tass you can do arbitrarily well. APX you can do a constant well, like for say 3/4 optimal, which by the way for max 3 set you can do, but you can't do any better than that. We don't know. Okay. LAPX means you can do at least 1 over C log X times opt. That isn't that good, but it's okay, I suppose. And PAPX is you can do 1 over P of X opt of X. It turns out that for clique, you can't even do that. Okay. We can find more classes that we're not going to. In fact, we're just going to deal pretty much with p-tass today. Okay. And it's known that, and it's pretty obvious that p-tass contains an APX, LAPX, PAPX. And if P is not NP, these are all proper. In fact, it's known. It is known. I won't prove any of this today. Max 3 sat, there is an approximation algorithm. It turns out it's 3/4. There is actually, it's pretty simple. There's a pretty simple algorithm that will, given a Boolean formula in 3 sat form, return an assignment that satisfies 3/4 times optimal of the clauses. So, for example, if it had 1,000 clauses in it, let's just say your formula had 1,000. Let's say you could satisfy 1,000 clauses. The algorithm will give you 750 clauses. That's not bad, but there's no p-tass. There's an actual limit to how well you can do. Right. Set cover, I won't define it here. You can do, and there's a log approximation to it, but you can't do any better than that. Okay, clique, as we saw, it turns out, yeah, is actually that you can't do it. Yeah, you can do poly approximation, but you can't do log approximation. And TSP, it turns out, you can't even do a poly approximation. So the point is that it's very nice. Also, it's nice that NP completeness for sets is sort of one thing. And in terms of sets, clique, TSP, set cover are all the same. But for approximation, they actually are different. So there actually is differences within NP. Okay, I'm going to skip all this. This is all formulas I don't really care about. Okay, yes, here we go. Okay, so rather than do formally, I'll just do it more directly. I'll prove the following. We're going to assume that max 3 set has no p-tass. Okay, I'm not going to prove that. That's a basic problem coming out of the PCP machinery. An independent set it returns the largest independent set of a graph. I claim the following. If independent set is in p-tass, then max 3 sat is in p-tass, and therefore p equals np. So that'll prove to us that IS is not in p-tass. Again, assuming p not np. Okay, so actually, as usual, this is better seen as a picture than an actual formal definition. So given a formula and epsilon, I'm going to form a graph as follows. Here's an example, and from it you can actually do the real graph. Okay, I want to prove that max 3 sat is less than IS for approximations. So you may have seen, this is actually a standard reduction for sets, but it works here as well. So what I do is, for every clause, I have a clique, a triangle actually. So x1, x2, not x3. And here we have x2, x3, not x4. And here we have just x1, x4, not x1, x4. Yeah, it's so we actually have a triangle, just a line. And then we connect all the variables that conflict with each other. X1, not X1, X3, not X3, X1, not X4. Realize, I know it's a pretty simple formula. A more complicated formula would be messy to draw, but this is what I do. Given a formula, I create this independent set. And now, okay, this graph. So, Eshwar, give me an independent set in this graph.
Just one question, Professor. So
Yeah.
in 3SAT, there will be 3 variables, right? In each class.
Oh, fair enough. I'm doing 3. Usually, yes, I'm doing 3 or less to make my picture not to be so messy. But you are correct. No, normally, it would be every single clause has exactly 3. I'm cheating a bit here, and one of the clauses have 2.
I don't know, Professor.
But no, I'm saying that no, you are correct. Max 3
Okay.
is defined as every clause has exactly 3. But for my example, to make it not messy, I am having one of the clauses have 2. But the point is still made. You could write the reduction will generally be for every single clause, you have a triangle, and then you connect up every variables from different clauses that conflict with each other, as I've done here. Now, with that in mind, I want you to give me an independent set in this graph. That is, give me a set of vertices that that share and that are not neighbors, that none are neighbors. The opposite of a clique.
Like x1 and x4.
X1 where? X1 in which triangle or which thing?
In the first triangle.
Fine, that's fine. So x1 in the left, x1 in the leftmost triangle. Very good. I'll see x4 here.
X4.
Good. And what else?
X2.
Yeah, that's great. That's great. So you picked out correctly x1, x4, x2. Realize you could so you picked out an independent set of size 3. Very good. I could set x1 true, x4 true, x2 true, and they don't conflict with each other. That would satisfy 3 clauses, correct?
Yes.
Yeah. Now, more generally, so imagine I had a much more complicated formula. If I have an independent set of size 17, then I have a way of satisfying 17 clauses. Do we see that?
Yes.
Yes, very good. Okay, yeah. So the point is, though, this reduction, you may have even seen this reduction before, but the point for now that's new for you is that it's exact. If you had an independent set of size 17, you'd have a max clause size 17. So if you could approximate independent set pretty well, let's just say you had an algorithm for independent set, which will actually output, say, 0.99 times optimal. Then here's what you would do. Take your formula, find this graph, apply approximation there. You will have found, say, 0.99 times optimal independent set. And then you can map it back to a satisfying assignment for the formula that satisfies 0.99 times optimal there. Do we see that? Eshwar, happy with that?
Yes. Yeah.
Yes, very good. And also, this is, have you seen this reduction before in this class or elsewhere? You may very well have. Eshwar, have you? Do you remember?
We have seen from SAT through 3SAT to max 3SAT, but not from, I believe, not from independent set.
Okay, fine. Okay, but the point is, though, that however, this is the kind of reduction you could show undergraduates in a class. My point is, usually it's shown as 3SAT IS, but I'm saying that reduction also happens to preserve number of solutions, and therefore it's actually very good for approximation algorithms. And realize that this reduction has this nice extra property that it actually preserves number of solutions, and therefore it's a good approximation. Oh, so Now, that's the easy part. The hard part was that max 3 sats hard to approximate in the first place. That was PCP. Once you have that, this gives you what you want. Now, realize, though, there's one thing about this I want to point out. Realize that the independent set, if I had a formula, well, okay, this formula, I could have a formula where x1 appears a lot of times, correct? I could have a formula where, can you imagine a formula, 1,000 clauses, where x1 appears in one of them and not x1 appears in 500 of them? Could I have? Yeah, I could have that. At which point, x1 would have degree 500, correct? That is, you can imagine a graph where some variable has very large degree. Okay. Yeah, this is not a hard concept. Yin Kang, can you see that? Can you imagine that if your formula had x1 in one clause and not x1 in 500 clauses, then your graph would have a point of degree 500. Yin Kang, happy with that?
Yeah.
Okay, very good. Okay, I am not happy with that. I'll tell you why. I want to prove that independent set is hard to approximate, even if every variable appears if every point has degree at most 4 or 7 or something like that. I want to prove bounded independent set. That is, independent set where every point has degree at most 4, say, is hard to approximate. So do you see that would not come out of this reduction? But I mean, so for that I would do more. Do we see that? Yin Kang, happy with that?
Yeah, right.
Okay, yeah, very good. Okay, so I'm not going to formalize stuff. Okay. Oh, that reminds me. Let me actually, while I'm thinking of it, put these slides in the chat. Oh darn, yeah. For some reason I have to actually stop sharing screen to put it in the chat. Yeah, there we go. Okay. Oh, let's see. 1, 2, 3, 4, 5. Okay. So okay, here we are. Where was I? Yeah, all reduction is fine. Okay, so let me go back here. So okay, so my goal is probably the rest of the lecture, I want to prove that the independent set problem with a bound on the degree is still hard to approximate. So how can I do that? Well, I'm going to need to go back to max 3 sat. This was max 3 sat, where I was certainly fine to have x1 appear 1,000 times, say, in various forms, that x1, not x1 appear 1,000 times. I want to prove that max 3 sat is hard to approximate, even if every variable appears only like 4 times. So I'm going to go for that's called max 3 sat -3. Yeah, so here's what I want to do. Yeah, max 3 sat is less equal to max 3 sat E3. Right. So here's my reduction. I'm given a max 3 sat formula. I want to output max number of clauses satisfied. Max 3 sat EA is every variable occurs at least at most A times. So max 3 sat 4 would be that, say, I could have X, not X appearing, or even X, not X, but I can't have 5 times where X appears. And I want to output the number of clauses you can satisfy. And you might, it's plausible, it's not true, but it's plausible that this is an easier problem. It's plausible, well, it is not obvious that just because max 3 sat is hard to approximate, max 3 sat 3 or 4 is hard to approximate. In fact, max 3 sat 1 is in P. Max 3 sat 2, I think, is in P. But the point is, though, I'm just saying it's not obvious and it comes up. Now, let me ask you a fun question, this is a question of opinion. Let's just say do you think the max 3 sat 4 problem is a natural problem that you really care about, or is it only a means to an end to try to prove independent set of bounded degree is hard? So Kevin, is that your name? Kevin?
Yeah.
Very good. Kevin, this is a question of opinion, not a hard question. Do you think max 3 sat 4 is a natural problem or is it a means to an end?
Not sure, but I think if you have a lot of variables and a lot of clauses, then this problem might be like useful, because in that case, some variables will appear in the clauses a few times. So then the problem is important in that case. If you have a lot of variables, then the problem is important, I think.
Okay. That's what I think what you're saying was interesting is, well, maybe I'm going to do a reduction today. And for our purposes, that will prove that max 3 sat 4 is actually hard. But what you're saying is, maybe using very fancy sat solvers, they can take advantage of only having 4 occurrences of X, and maybe it's actually easier in a practical sense. Okay, fine. So we want to prove max 3 sat less than max 3 sat 3. Oh, actually that's going to be 4, I think. Well, we'll see. Anyway, I am first going to show you I'm going to show you a reduction that would work for sets. If you cared about 3 sat and 3 sat 3, this reduction would actually work, but I'll show you why it doesn't really work for us. And it's easy, by the way. You'll be happy to know. Yes, I know that. I'll be honest with you. Last lecture, PCP and clique, that was kind of hard. This will be easier. Okay, so here's a bad reduction. That's not going to work. That's good. That would work for sets. Does not work for approximations. Given phi of x1 xn, assume it has m clauses. Each variable occurs. For each variable that occurs at least 4 times, I want to have it appear 3 or less times. So I'll ask you the question. How would you take some variable that appears 10 times and get a formula that's equivalent where it appears at most 3 times? Your thoughts? Amin, any thoughts on how you would do this?
Maybe somehow increase the number of clauses.
Okay, so that's true, but how do you do that? I mean, so x, let me see. Yeah, x, k occurs, x occurs k times. X occurs k times. I'll have variables z1 through zk, and what will I do with them? Anyone? Oh, go ahead, Amin. Can't tell. Amin, you're muting, unmuting. So do you have an answer or not?
Oh, sorry. Maybe like if we introduce more variables, we can just wherever it appears, like we replace like x by z1 4 times, and then the second the next 4 times it appears, we replace it with another variable.
That's correct. That's
and
great.
Then then we introduce maybe some clauses to make sure that those variables are equal.
Indeed, we do. Yes, very good. Well, we would have the clauses z1 implies z2. Remember, implies can be written as ands and ors. So z1 implies z2, z2 implies z3, etc., down to zk implies z1. Okay, very good. So are we happy with that? So first off, does this reduction? So certainly the good news is an output phi prime, and indeed we do have. Okay, so is everyone happy with this? Okay. Then the good news is this does work. Phi is in sat if and only if, actually this should be phi is in 3 sat if and only if phi prime is in 3 sat 3. We have taken a 3 sat formula where x could appear in a lot of places and replaced it with a 3 sat formula where x appears at most 3 times. Are we happy with that? Every variable appears at most 3 times. Happy with that? Very good. Caveat, we need to be able to take an assignment that satisfies. Now, our concern is, we want to say if a formula in phi prime satisfied many clauses, then a formula, then we can actually map it back to a way of assessing phi with many clauses. So here's a bad example. Here's why it's not really a good reduction. Let's look at this formula here. Rather simplistic. X or X or X, X or X or X, etc. So how many clauses can you satisfy? Well, if X is true, and there's going to be M of these clauses. So there are 2 M clauses total. So we can satisfy at most half of them, at most M of them. Do we see that? If X is true, the first M are satisfied, but the last M are not, and false otherwise. Okay. So next slide has phi prime. This would be phi prime. As Amin said, we should do correctly. We'll substitute all those x's with z1, z2, z3, etc. And then later on, not z3m plus 1, not, etc. And we also have all of these. There is now 6m. There are now 6m clauses. No, sorry, 6m variables. And we have z1 implies z2, etc., etc., etc. So do we see that? Do we see that this is the result of your transformation?
I agree.
Very good. And we would like to have the case that, oh, if I can satisfy a lot of clauses of this formula, then I can satisfy a lot of clauses of phi. So, Kevin, do we see that? That's our goal. We'd like that to be the case.
Yeah.
Yes. Now, unfortunately, it's not true, because realize we can satisfy a lot of clauses of this formula. I can set z1 to z3m to all be true. I can set z3m plus 1 to z6m to all be false. And these imply signs that we're supposed to make them all get the same value, all I've got to do is break one of them. So z3m implies z3m plus 1 will be false, but everything else is true. So I can satisfy 8m minus 1 clauses. That is, of the 8m clauses, I can satisfy all but one of them. I can satisfy, oh God, it's not even a fraction, it's more than a fraction. It's virtually every single clause, but I can only satisfy half of the clauses of, max 3 sat, I can satisfy half the clauses. Max 3 sat phi, I can satisfy half the clauses. Phi prime, I can satisfy all but one of the clauses. That doesn't seem too bad, but wait, actually that does seem pretty bad. The point is that, so I really can't use this solution for max sat phi prime to help me with max sat phi. Do we see that? So this is a bad reduction. This reduction does not help. This reduction, Amin, good as and bad as for you. Amin's reduction did give us that as sets 3 sat is less equal to 3 sat 3. That's great. But it does not give us anything about approximation. So do we see that? Okay, Yin Kang, do we see that?
Yeah.
Okay. And does that make you happy or sad?
I'm happy because we need to use some like more fancy techniques.
Yes. And you should be happy that you should all be happy that you're enlightened. Yeah. Okay, so I'll skip this. The point is that when we replace z1, z2, z3, etc., we intended them to all have the same truth value, but we didn't really enforce that. Well, we did try to enforce it with imply signs, but the trouble was that here's what we're going to do. So the trouble is, we benefited from breaking the equivalent. We benefited from saying, no, I'm willing to sacrifice one clause for the good of many clauses. We're going to have z1, z2, z3, the enforcement to make them all get the same variable, same satisfying assignment. We want to have the enforcement mechanism also makes that you're better off making them actually the same. Yeah, say it more carefully. Here, to break the rule, to break the intent, you can break the intent, and here it made you able to satisfy more clauses. We want to have it that if you break the intent of making all the zi's get the same value, you're actually worse off. So okay, you could view it as cycles. We have z1, z2, z3, etc. Back to zm, all in one big cycle. We're going to use a more complicated graph than a cycle to sort of bind them together better. So we're going to have like z1 and z2 are equivalent, and z1 and z3 are equivalent, and z1, and in various funny ways. We're going to do, and here's what, this will make Yin Kang very happy. Yin Kang wanted a more complicated reduction. He'll have one. We're going to use what are called expander graphs. We're going to use what's called a d-expander. A d-expander is every vertex has degree d, so a 7 expander, every point has degree 7, or less actually is fine. And also, if you partition the vertices into 2 sets and take the set of edges between them, it'll be at least as big as the minimum size of them. Realize a cycle does not have that. If you have a cycle, and you break the vertices in two halves, if I have two vertex sets, then you can have very few edges between them. Here we're going to insist that if you break up the vertex set, there are lots of edges between them. Okay, and so first off, do we understand what an expander graph is? Happy with that? I'm not telling you to construct one. In fact, constructing these is actually difficult, although you can do it in polynomial time. But I'm just saying that they exist. Well, we'll go to that in a second. But do we see what they actually are? Eshwar, are you surprised they exist? Eshwar, yeah.
I have heard about it, but I don't know what exactly now. I understand.
Let me tell you why it might surprise you. The first, when I tell you, if I told you every vertex is small, has small degree, you might think, oh, the graph doesn't have that much connectivity. That is, it's kind of a sparse graph. However, then I tell you, every partition has a lot of edges. So the weird thing is, item 1 is telling me it's kind of sparse. Item 2 is telling me it's kind of dense. So I'm not saying it's a contradiction. I'm just saying that it is perhaps surprising they exist. And in fact, the first constructions of them were probabilistic, but we now have ones that are polynomial time, and they're very clever. And we're going to use them. We're not going to actually write any down, but we're going to use them. Okay. Oh, and it's known that for k even, I don't care about that. There exists 3 expander graphs. That is, there exists a for every even number k, 1,000, 2,000. There exists a 3 expander graph. So a graph where every vertex has degree 3, but if you break up the vertices into 2 sets, then the number of edges between them is actually bigger than either set. Okay, now, and I'm going to do now max 3 sat less than max 3 sat 7. I'm going to take a formula, and I'm going to actually replace every vertex similar to what a mean did, although I'm now going to have every variable appears at most 7 times, and I'm going to have that if you could approximate max 3 sat, the phi prime well, they can approximate phi well. Essentially, if phi prime has, you can satisfy lots of clauses, then phi you can satisfy lots of clauses. So input is x1 and xn, like before. If x appears k at least 8 times, we'll use 8. Then I have variable z1 is zk. We'll assume k is even. I don't care about that. Now, here's what's interesting. What a mean did was he connected up z1 and zk in a cycle. We will actually replace. Well, we'll first replace the k occurrences with z1 and zk as usual. Here's the key thing. Let G be an expander graph on k vertices, 1 through k. I will add the edge ij and the clauses zi implies zj and zj implies zi. So take an expander graph and think of putting on k vertices, think of putting the variable z1 and zk on each of the vertices, and whenever there's an edge between I and j, you put in the zi implies zj and zj implies zi clauses. Okay, so before I say why this is a good thing, do we understand the construction? Modulo understanding expander graphs. Okay. And notice the good news is zi will occur 7 times in phi prime. And the good news is, the usual thing, once in the plate, every x occurs, so, every zi, so realize, so why 7 times? So take z12. Z12 will actually occur in the formula where some x was, but it also will look at z12 in the expander graph. Well, it has degree 3. It has degree 7. So sorry. 7, Sorry, 3. No, it has degree 3, In the expander graph, z12 has degree 3. So you'll have z12 implies things and implied by things. So it's actually because it has 3 things coming out of it, that'll give you 6 more vertices. Yes. 3 times. So we have zi implies zj. We'll have that 3 times. So that'll give it degree 3. So we have every variable has degree 3. Every variable occurs 7 times. Okay, that is Z1 implies three things as implied by as implied by three things. So we have every variable occurs at most 7 times. And we clearly have, yeah. So we also clearly have that that phi is in 3 sat if only phi prime is in 3 sat 7. Now the question arises, I now claim that if the phi prime has a lot of satisfying assignments, then phi has a lot of satisfying assignments. So let's see why that's true. Okay, so and more importantly, here's what I really want. Given a assignment for phi prime, I want to map it back to an assignment for phi that again satisfies a lot of clauses. So B is an assignment, and X occurs less 7 times. If X occurs less equal to 7 times in phi, then X in phi prime is untouched and give it the same truth value. Now, here's the really important point. So X occurred 84 times, whatever, in phi. Now in phi prime, we have Z1, Z2, etc. I want to show that in the truth assignment for phi prime, I am better off making all the ZIs get the same truth value. So, yeah. Let's just say we have Z1 as ZK, and they were assigned this. Okay, if they're assigned the same value, that's great. Let's just say that they were assigned different values. We have, yeah. Okay, well, the intuition is if we actually assign the same value, that's very good because that will make a lot of the edges in the expander graphs, the clauses they're associated to, more of them are set to true. And we want to show that you're worse off if you flip it to false. Well, let's actually just do it first, though. ZT is a subset of Z1 and ZK that are assigned true. ZF is a subset that are assigned false. Okay. And we want to say we're better off assigning them both the same. We'll assume that more are assigned true than false. I guess it's similar. Here's what let me actually recap all this. I have an assignment for phi prime. Z1 through ZK, some were assigned true, some were assigned false. I want to show you're better off. You'll satisfy more clauses if they're all on the same team. So we'll assume that there more were assigned true. We'll now prove that if you flipped all the falses to trues, you're ending up satisfying more clauses. So the expander graph has, remember, we have ZT and ZF. So the expander graph has ZF edges, at least ZF edges between ZT and ZF. That was the definition of expander graph. Okay. Now, take every IJ between ZT and ZF. There are 2 clauses, ZI implies ZJ and ZJ implies ZI. Right now, these clauses are set to false. If you were to make every single element of ZF true, then you're adding 2 times ZF clauses. So you're adding a lot of clauses to be true. Yeah, that is, all those clauses are now true. We're adding, so the good news is we're making 2 ZT more clauses, 2 ZF more clauses true. That's good news. The bad news is that indeed you may be also tinkering with the original formula, but it turns out that, yeah, if all the clauses Z and ZF are set to true, then we have 2 ZF clauses more switched false to true. That's good. But we also have, oh, I actually set these to false. Well, then most ZF clauses from the original one are true to false. My point is net gain of ZF clauses. So in a nutshell, the number of clauses you set to true from the expander graph point of view is actually more than those that you lose from the original phi. So therefore, you're better off making everything in ZF true. So the point is that, we have rigged it so it is to your benefit to actually make all the ZIs the same truth value. And therefore, we can intelligently say, all the ZIs, X was a variable in phi, Z1 to ZK, where its copies in phi prime. They're set to the same value. That's the value I'll use for X. So happy with that. Okay. And I'll recap and nitpicks. Oh yeah, so that gives me 7 times. So I now have every variable occurs 7 times. I now need to actually get 3 times. Turns out that I originally wanted to get down to 3. So max 3 sat 7, that reduction to max 3 sat 3. Turns out for that one, you can use the cycles I had before without a problem. Okay, I won't go into detail on that. But what's the benefit of all this though? Now, here's the important thing. First off, we have max 3 sat 3. We can now go back to our independent set problem. Let's see now. In fact, let me actually go back to that directly. Let's revisit this. Now, recall this reduction. I now want to prove that independent set with degree bound 4 is actually hard to approximate. Imagine you had max 3 sat with 3. Yeah, max 3 sat 3 would be a formula where every variable occurs at most 3 times. You could then do this reduction. What will the degree of a vertex be? Well, let's look at x1. x1 will occur in this triangle, but also it'll actually go, let's say you had x1, let's see, it's degree 3. So you could have, for example, x1, not x1, and not x1. Right? You could have x1 appearing once, not x1 appearing twice. You'd have x1, not x1, 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 and x1 here. So you'd have degree 1, 2, 3, 4. So if max 3 sat has every variable occurring at most 3 times, then the graph will have each vertex have a degree at most 4. Do we see that? This part's easy, so this one I actually want my own board for. So max 3 sat 3 reduces to IS 4. Okay, Amin, happy with that?
Yep.
Okay, very good. Okay, so we now have, the reason we went through all that expander graph stuff was that before we had IS was hard to approximate. Now we have that IS even with bounded degree is hard to approximate. Okay, so first off, we can now use this for many proofs that problems are hard to approximate on bounded degree graphs. And these proofs will now be very easy. No more expander graphs, no more PCP, we have it. So there's a general lesson here, in general though, is that once you have some very basic problems are hard to approximate, or in this course earlier, hard to actually solve, you can then use those to get other problems much easier. As an analog, I'm not sure if you've seen the proof that SAT is NP complete. The proof that SAT is NP complete actually uses Turing machines. It's not really hard, but it is somewhat grubby because, for example, Eshwar, to prove SAT is NP complete, could you use a known NP complete problem? Early on in this course, some other course, when you prove SAT is NP complete, can you use a previously, to prove clique NP complete, you use SAT, fine. To use SAT NP complete, can you use a previously known problem? Eshwar, can you?
Yes, but I don't know which problem.
No, you can't.
I mean,
no.
Yeah.
Here's the funny thing. No, you really can't. There's going to be a first NP complete problem. You're correct in saying, once you, in this course and maybe some other courses, you have a large set of NP complete problems to draw upon, 3 coloring, max 3 sat, whatever. But when you prove the very, very first problem NP complete, you don't have that. So in fact, Eshwar, I'm guessing you've never seen a proof that SAT is NP complete. Is that correct?
yes.
Because you can't use clique or 3 coloring. It turns out that you have to go back to the original Turing machines and you code Turing machines into formulas. Now, it's not hard. I mean, you could do that. I'm not going to do it here, certainly. But the point is, though, that makes the problem very basic. Once you have SAT, you can then get all this other stuff. And you've seen the other stuff more. My point is that similar here, once we have max 3 sat, clique, and max 3 sat bounded number of variables, once you have that, those were hard and basic. Once you have that, the rest are much more standard things you're used to. Okay. And also, it turns out the machinery used for max 3 sat 3 is used elsewhere, but I'll skip that for now. Okay, now, so delta of G is the max degree of a graph, fine. This one I just did. Independent set D, A, is degree less than equal to A. We just proved ISB 4 is hard to approximate. Vertex cover bound A, you can guess. Dominating set bound A. And we'll show that, we show that for some constant A, all of these are APX complete. Ignore that. All of these are hard to approximate, or more to the point, they don't have a p-task, or if they did have a p-task, then P equals NP. So ISB4 is APX complete, APX4. Oh yes, also it turns out that I proved it was actually, you could not approximate it well. Yeah, I proved it has no p-task. Turns out it does have a constant approximation. IPS delta is delta plus 2 approximable. So in fact, we get that IPS 3 you can 2 approximate. That is, there is an algorithm that will, given an ISP 3 graph, a graph with a degree 3, there is a way to 2 approximate it. That is, you want an independent set of size, you want a small one, large one. It's kind of backwards. I'll just say it's actually more like a half approximation. You want an independent set of size. The best one is size 1,000. You can get one size 500. Fine. Okay. So ISP4 is APX, and therefore it does not have a p-task. Can it be lowered? Can the 2 be lowered? We're not sure. Okay, it might be open. Okay. Now, vertex cover is hard. I'll prove ISP4 is less than vertex cover 4. That's the usual one. Map G to G, and a vertex cover for G is a vertex cover for G is an independent set. Its complement is an independent set for G. So there, it's not even a reduction. It's just the same graph. Although you modify what you're looking for. Yeah, we can map the vertex cover for G back to an independent set for G exactly. So that I'll skip. Okay, and oh yes, vertex cover is interesting. Vertex cover, here I can prove that vertex cover degree 4 has a constant approximation. More generally, vertex cover has a 2 approximation. That is, you can, given a graph, you want a small vertex cover, you can always, there's a pretty easy algorithm that will give you a twice optimal. So you have a graph, you want to know its smallest VC is of size 12, you can find one of size 24. Can you do better than that? Here's what's really fascinating. Vertex cover has a 2 approximation. That was done in 1979. People have tried to prove it does not have a 1.9 approximation. People have been unable to improve the approximation and unable to prove it's optimal using P equals NP. But it turns out that using a different hardness assumption, what's called the unique gains conjecture, you can get that 2 is optimal. Okay. But however, it's open. Okay. Dominating set of size 8 is APX. Oh, I'll just say, let me just get to here it is. You want to know a vertex cover for this set. It turns out, take every edge and add to it, use it to add other vertex, AB, AB, BC, BC, CD, CD, etc. And it turns out, I'm running out of time, so I'll just do this quickly. It turns out that if you have a large dominating set, if you have a small dominating set of this graph, can be mapped back to a small vertex cover of this graph, and it's exact. So yeah, therefore, if you have an approximation for dominating set, you can apply it to this graph, map it back to a good approximation for vertex cover. So and it turns out it's degree bound 8. So we now have independent set degree 4, vertex cover degree 4, dominating set degree 8 are all not just hard to solve, but hard to approximate as well. Okay. All going back to max 3 sat 3. Okay, and that's known to be actually in there. Okay, fine. Recap. I think I'll skip all this when we get to we'll just get to some nice summary slides. Okay, that's not very interesting. Okay, so there are many more. Okay, so I'm now just going to list more problems that are hard to approximate. that is more problems that don't have a p-task. Okay, this is the kind of problem Eric likes a lot. A set of unit squares. You're given a set of unit squares with the edges colored, and you want to put them into a rectangle with the edges matching. That is, you want that if some squares right edge is red and some squares left edge is blue, you can't put those edges next to each other. That problem is actually hard to approximate. That's called edge matching puzzles. Edge match puzzles. Okay. And question. So yeah. So is there a packing of the squares into a rectangle such that all the tiles sharing an edge share that edge? Okay. That problem is hard to approximate. Okay. By the way, that's also interesting because it turns out Eric's done a lot of work on jigsaw puzzle problems, how to approximate or how to solve, and this helps you solve those problems. It turns out that jigsaw puzzles are hard. That is, one can show that jigsaw puzzles are hard using complexity theory, that are NP complete, and how to approximate like this using max 3 stat 3. Okay, here's a strange one. You're given a 3 regular graph. That means every vertex has degree 3. And you're also given a 3 colored edges. That sounds like you're given a lot. Okay. Find the largest independent set. So this is really interesting because given a graph, find the largest independent set. That's hard, fine. But even if the graph is regular, every graph degree exactly 3, and even if you're also given a 3 coloring of the graph, maybe that's useful. Can you find a large independent set? No, that's hard too. Okay, 2-dimensional matching. So given 3 sets, A, B, and C of size n, and given a subset of triangles like A, B, C pairs. Okay, intuition. Aha. So imagine a species, Martians. Martians have 3 sexes. Let's see now. I'll call them A's, B's, and C's. And in order to actually have a child, one member of A and B and C must get together. And so the question arises, we're trying to arrange n 3-person marriages. Right? And can you do that? So the question really is there an M prime so that all triples are disjoint, so no polygamy, and also every element of every person is matched up, so no one's unmarried. And it turns out that problem is also hard to solve, hard to approximate. 3-dimensional matching. It was, by the way, one of the first problems shown in NP complete, and it's useful for other problems. Okay. Okay. And yeah, we're trying. Oh yeah, and in the approximation version, we're trying to maximize the number of matches. All right. Oh yes, and I'll end with metric traveling salesperson problem. So given a weighted graph, I want to find the TSP for it. I want to find the lowest cost Hamiltonian cycle. A weighted graph means that the weight of the distance from A to C is less than AB plus BC. This question has interesting history. There was a 3/2 approximation for it back in 1979, and people thought that was optimal. And people did prove it had no p-task, that is, you can't get arbitrarily well. People thought 3/2 was the actual answer, but about 2 years ago, people in, I think it was Wisconsin, they proved 3/2 minus like 1/2 to the 40th, some absurd improvement. So 3/2 is not the answer. We don't know what the answer actually is, but for our purposes, though, you can't do arbitrarily well with TSP. Okay, I will now. That's the end now. So Mohammad, Mohammad's going to end the recording soon. But any questions on any of this stuff? They can be very general questions. The takeaway here is that once you have max 3 sat is actually hard to approximate, you can then get max 3 sat 3 hard to approximate, and from that, lots of other problems, including problems on bounded degree graphs. So questions on any of that, high level, low level, as you see fit.
Yeah, and I think the hardness, actually, the people at UW, there was a group from UW that they had better than 3/2 for the TSP.
Okay, yes, that's right. Okay, more thoughts? Okay, then thank you for your attention and stuff. Okay, and Mohammed, you can shut the recording off and we'll call it a day.
Yeah, thanks a lot, Will. I think
Thank you.
It was great, and then will be recorded and the people can use it.
Very
Okay,
good.
that sounds good. And yeah,
Okay,
bye
very good.
everyone.
Okay, bye.
Bye.